So here we're going to look at our nitrogen connected to our carbon structure and how that's going to affect our substitution and potentially our elimination reactions. Because remember, that's what this chapter is about. So if we're going to put a nitrogen on our carbon chain, what we want to do is think about that chemistry. What chemistry is available to that individual species? So to address that, we need to look at its reactivity. First and foremost, it does have that lone pair, which means that nitrogen could act as a nucleophile and or a base. It is electronegative, so we might consider that the electrons get pulled away from either the hydrogen or the nitrogen. However, it isn't electronegative enough, and it turns out that balance, and this is one of those kind of tricky things, that balance of electronegativity isn't there to support that, and what ends up happening is that the nitrogen isn't a good enough leaving group, okay, so or stable negative charge, which means we don't get access to that hydrogen being acidic, and we certainly don't get access to the carbon being electrophilic, which means this structure really only leaves us with that nucleophilic or basic characteristics. And if you have to move into biochemistry, that basic characteristic of nitrogen is going to become problematic because that really dictates a lot of its standard chemistry. But it does have some nucleophilic character, and because it is a nucleophile, it could potentially get used in substitution. If we consider reactions to enhance or stifle that chemistry, if we wanted to make it act as a base, we could throw in an acid. If we wanted to make it act as a nucleophile, we could throw in an electrophile. So deciding which of those chemistries wins really comes down to the reagent that we're going to see. Because acid-base chemistry is boring, let's look at substitution. So let's make it act as a nucleophile. So to go ahead and do so, we need to throw in an electrophile, and what we would see is a reaction similar to this. Our nitrogen, being a decent nucleophile, would backside attack in this case, ejecting that bromide leaving group. We'd get an acid-base reaction happening, so we need two equivalents of ammonia to allow this reaction to occur. That's going to deprotonate the forming ammonium ion. That species there is our ammonium ion. And because it is now acidic because of that hydrogen, that's where our free-floating leftover ammonia will come in, deprotonate, and we'd be left with the primary amine. And there we go. We'd say we've run a substitution. But it's second semester, and because it's second semester, nothing should be looked at just face value, and we should dig a little bit deeper. So let's dig a little bit deeper. Let's compare our starting amine to the ending amine, because really the functional group is still the same. It's an amine, either with hydrogen or with carbon connected to it. So that's really our difference. We're looking at hydrogen being connected to it to start with versus carbon being connected to it to end. Okay? Well, why does that matter? Well, what is the difference between carbon and hydrogen? Carbon has more electrons. If it has more electrons, there are more electrons potentially being shuttled towards that nitrogen, which means that nitrogen, in particular that lone pair, becomes more active than the starting material. Why does that become important? Well, the reaction runs once, and we now make a more active species than we started with, which means the more active species now reacts. Okay? Which means if we were to look at this at a much larger scale, once we've run it once, we still have that starting bromide floating around. We still have the NH3 floating around. And so once it's happened once, that's our reaction solution. And in that reaction solution, the primary amine is actually going to be more active than the NH3, which means the very next reaction to run is this one, which means we would now get, again, this nitrogen with two hydrogens, positive, and now that carbon structure and more bromide floating around. But I would now get a secondary amine. Another equivalent of amine can come in and remove that hydrogen. This becomes the problem with nitrogen. while it's neat and has its nucleophilic and basic characteristics, that nucleophilic chemistry is reborn, if you will, at the end of one reaction cycle. And not only reborn, it's more active than it started, which then means this is a horrible synthesis. We're not going to be able to make primary, secondary, or tertiary amines. They just aren't going to work. So if we try to run this reaction, even with one equivalent of ammonia, what we end up with is this massive difference in products. And that 57% for our primary amine isn't a horrible yield, okay? And it's definitely not great, okay? But that 57% isn't great, but it's also not horrible. What makes this reaction particularly horrible isn't that that's a 57%, but that this 24% and this 3% have virtually identical chemistry to the primary 57% yield. Because they have identical chemistry, those two species are virtually impossible to separate from the primary amine. Which means, yes, I may produce a half-decent yield of my primary amine, but I have virtually no way of purifying it. It doesn't matter how good your yield. Well, if you get a 99% yield, that's pretty good. 1% impurities isn't too bad. Okay, but in this case, that's a lot of impurities to be dragging along, and we don't have an easy way of removing those because, again, their chemical properties are all the same. Okay, so really the lesson that we're getting here is that when we look at amines, we really only have access to them acting as bases. While they can act as nucleophiles, we actually don't want them to act as nucleophiles because that chemistry is just a mess. Or is it? Okay. Why did it not yield just the primary amine? Well, the primary amine was also a nucleophile, and so it could continue to react. Well, if we look at that overall reaction, what changes could we make to ensure that we only get one product? Okay, and usually I get people shouting out in class suggestions, which is awesome, but you can't do that now. And one of the first suggestions is you control the amount of starting materials, which is a neat idea, but these amounts are already controlled. They're set at one equivalent. Okay, and even if we did that, that doesn't fix the issue that the primary amine is equally active, if not more active, than our starting amine, which means we'll get some amount of the secondary and tertiary. Okay, so how can we ensure that we only get one product? Okay, well, that one product is really going to come down to looking at these products and deciding which of them is different from the others. That would be the tertiary, or not tertiary, begins with 4, quaternary. Our quaternary amine. Why is that one so different? Well, what happened to the lone pairs associated with the nitrogen? There are none. In each of the other cases, there are implied lone pairs to satisfy the octet of nitrogen. In the quaternary amine, it already has its satisfied octet, which means there are no lone pairs. It is not a nucleophile. It cannot react more. So how could I change the conditions to force just the quaternary amine? Hopefully what you've come up with is that I add a crap ton of the alkyl halide. The alkyl halide as the electrophile, if I just add a ton of it into solution, okay, it doesn't matter which amine I make, there's still more alkyl halide to react, and I can fully saturate all of the nucleophilic sites on that nitrogen. Okay, so that's going to be how we drive this, and that's going to get us to the quaternary amine, which would then address the next question: why? Why do I want the quaternary amine? Well, let's take a look at that. Okay, do we want the nitrogen to be positive? If we went back and looked at our oxygen, we protonated the oxygen, and what did that do? That turned this into a great leaving group. Well, does nitrogen want to be positive? Similarly to oxygen, no, it's a little bit more okay with it than the oxygen due to electronegativity differences, okay? But it still doesn't want to be positive. That means we have a good leaving group, okay? So great. we have a good leaving group. What can we do with a good leaving group? Well, what reactions gave us leaving groups? There were two: substitution and elimination. Okay, so could I run a substitution reaction with this now? To do that, I would have to add a nucleophile. So if we go through and draw out what I'd be looking at, those are all CH3s, right? 3 positive. Could I now add a nucleophile into this solution so that it could come in and chase that leaving group off? Okay, it's not as good a leaving group as the oxygen because oxygen was more electronegative, which means we're probably going to have to force this structure off. That means needing a strong nucleophile, which would mean SN2, and that becomes problematic because that is a giant steric snowball of a mess. Okay? Which means when we think about the two reactions that were possible for this, both substitution and elimination, the substitution isn't likely due to all of that steric hindrance, which means instead we want to push an elimination reaction. To push an elimination reaction, what conditions usually help? So heat, usually a good signifier for it. We have a somewhat decent leaving group. What else is typically a signifier? Usually a base, and usually a strong base. We could identify that as a strong base by drawing that negative on there. So now we would expect to run the elimination, and we would go through and we would remove a hydrogen from the beta position to go through and form our final product. Okay? For those of you that have read ahead, you're probably shouting but. For those of you that remember elimination reactions and remember that when we run an elimination reaction, we have to be aware of all of the beta hydrogens, should also be screaming but. Okay? Which just sounds stupid the more I say it. It sounds like everything I say. So our base could have equally removed a hydrogen from out here, which means we get two potential products. And so this is where we should again reflect back to what we've learned about elimination in the past, and we should acknowledge that the purple one is more stable, and because it is more stable, it should be the more likely product. Okay? It should be thermodynamically favored. That's a loaded word, isn't it? Okay. The green one is less stable and therefore less likely to form. Okay. However, when we run this reaction, what do we see? We get the less stable product. And that is exceptionally weird. Okay. Why does that happen? Okay. If we think back to elimination, you might hear that referenced as the anti-Zaitsev product. Okay. A good colleague of mine in our tutoring center has said that anti-Zaitsev is probably a bad word because anti has lots of other connotations, and it's probably better to remember this as not Zaitsev so that you don't get the anti involved in this. We're going to get the anti involved in a second. But remembering the overall reaction is not Zaitsev is probably a better way to memorize this. So, because it's not doing what we expect it to do, of course it gets named. And this type of elimination is known as the Hofmann elimination, which I'm probably going to misspell because I can't remember how many F's and N's are supposed to be in there. Okay? And what this is effectively saying is that we get the least favored or the least stable product forming out of this. Okay? And we don't just get to name it because something happened when it shouldn't have, or we get an unexpected result. We also have to be able to explain why it did that. And that becomes much more challenging. Okay, so what we're going to do is look at another drawing. And in this case, what you might notice is in this explanation, we have to move to Newman projections. And our textbook has done a really good job illustrating this. But that's not easy to see. This is why you should pull out your model kits so that you can try and visualize this. And I'm going to attempt to do this with my model kit so that you can see what's happening. If we're looking at these reactions, okay, so let's kind of animate this, or not animate, but color it out. green 1, 2, or purple 2, 3. When we look at the green one, we're doing our elimination with a hydrogen here. When we're doing the purple one, we're eliminating with a hydrogen here. Because it is an E2 elimination, we have to be concerned about the complications of the E2. And the big complication of the E2 mechanism is that we have to be anti-periplanar. Okay? Which means when I go through and look at this structure, the hydrogen has to be anti to the leaving group. Okay? That is a requirement for the E2 reaction to happen. So if we go through and look at the drawing that we've got down there, that's what I'm attempting to show. Note that our leaving group, that nitrogen, is aimed upwards, and the hydrogens I've drawn are aimed downwards. This gets a whole nother layer of complexity behind it because that carbon at position 2 is a stereocenter, and so we should really draw this out a little bit differently. And I'm just going to say that that nitrogen is aimed, and I have to align my structure that I'm going to play with here in a second, wedged, and hopefully I did this right. Okay, and there are my CH3s. We've got the hydrogen aimed down. Note there are 2 more hydrogens out there, which I wish I could kind of ghost, but those aren't relevant. What we're concerned about is this one. And actually, we got to get a little bit more specific, so I'm not going to say that one yet. And then we also have these hydrogens. If we have to be in that anti-alignment, we have to be concerned with drawing our structure correctly and ensure that to be anti, that hydrogen has to be dashed away. So if it is dashed, this hydrogen's coming at us, and then that hydrogen's in the plane of the paper. If we go through and look at the other side, this hydrogen must be dashed, this one must be wedged, and now we could run our elimination. And you might say, well, I don't see anything that would necessitate why that would be important. Okay? Unfortunately, for me to show you the image, okay, or the kind of the model kit, I have to get rid of the drawing. So the drawing's about to disappear, and hopefully what I can do is also live, wait, look at that, make my picture a little bit bigger. And so if we were to go through and look at that model kit, or our model, I believe I've got this drawn out correctly. So there's our butane. Okay. There's the nitrogen atom aimed at you. I do apologize for the silver atom there. Don't stress about that one. Here are green hydrogens. That would have been nice to color code on these. Here are our purple hydrogens. Okay. So what we want to do is ensure that our hydrogens are anti. So if we go through and look at this, we're going to say, well, isn't this hydrogen, our purple one, anti to the nitrogen? Well, to see that, we would have to turn the model. There's our nitrogen. I'll go ahead and hold my hand on it. And there's the purple hydrogen back here. Are those anti? No. To be anti, it would have to be here. It's kind of hard to do in the camera. Okay? What we should now realize is now we can do the elimination. But now we also have to consider something else. We have to consider what we learned about Newman projections. Okay? And actually, I just realized, let's not worry about that. We have to worry about Newman projections. Is this Newman projection a low energy Newman projection? So what type of projection are you looking at? Well, we've got where my amine is, that's a group hanging off, and then we have that 4th carbon in the butane chain up here. Those are on the same side. These are definitely eclipsed, staggered, but those 2 groups are very close to each other. And since they're the largest groups, that group wants to rotate as far away as possible and become anti to it. The instant it does so, what happened to those purple hydrogens? They're no longer anti to the leaving group. And because they're no longer anti to the leaving group, what happened to the success of our elimination? Well, it can't eliminate. Okay? So if we were to form the purple, more substituted structure, we would have to move to a very high energy intermediate. That requires a lot of energy to get there. So we'd have to heat the reaction up a lot to force that. It's also not going to form fast because I have to clear that activation barrier. Okay? So that was our purple. If we look down the 1,2 bond, so now I'll turn the model again. In theory, we've got this aligned the way I drew it. Here's our 1,2 bond. I'm totally holding it backwards. I apologize. There's our 1,2 bond again, okay, in here. I don't know if, maybe my pencil. There's the carbon 1, carbon 2. And I now want to sight down that. So now when I look down that, the nitrogen leaving group is going to be on the back carbon, okay? And if we look, I'm in a horrible Newman projection, because the Newman projection we're now looking at would be what? Good, eclipsed, okay? That eclipse conformation is unstable, so I need to rotate just a little bit to make sure it is now staggered. In that staggered conformation, boom, there's a hydrogen that is now anti. Well, maybe I did a bad rotation. Maybe I should have done it this way. Still a hydrogen anti. Or this way. Still a hydrogen anti. Note that because all three of those are hydrogens, all of them have the same steric repulsion here in any one of those rotations, and it is a less steric repulsion than if we'd gone to the 2,3, attempting to go slowly, where we have a carbon versus the nitrogen. Okay, so it is that repulsion that forces the Hofmann elimination to happen to the least substituted pi bond, or making the least substituted pi bond. Okay, and because I really like our book and the job they've done at animating things, we can go through and look at that, and I'll try and draw through some of these kind of discussions on what we're seeing here. So, when we look at that 2,3, there's the methyl and the amine butting up against each other in that gauche alignment. That would allow for the removal of that purple hydrogen, but we're now in a conflicted state. If we rotate that methyl so that it is no longer sterically impacting that nitrogen, we now have lost our purple hydrogen to eliminate. Okay? Our purple hydrogens are now not anti to our leaving group, which means we can't get the base in to do the elimination. If we look down the 1,2 bond, well, now things change around a little bit. Okay, there's the same deal with our leaving group, and now when we look down the 1,2 bond, we have that green hydrogen immediately aligned in that anti-alignment. Note, we still have green hydrogens out here, but those hydrogens are smaller than the methyl group. So they have a smaller effect on the elimination state itself, and we increase the odds of running the elimination that way, which is why we get the elimination favored towards that direction, and we end up getting the anti-Zaitsev result. Okay, so neat little reaction. 90% certain that's the end of it, and it is. Thanks for listening. Hopefully that helped. Remember, pull out your model kits.